In this first lesson, we will look at the primary requirements of all aeroplanes and introduce the four forces acting on an aeroplane in flight. From some of the very first aeroplanes to today, the primary requirements of an aeroplane have remained the same. These are a force, lift, which enables the aeroplane to fly in the air, a safe and protective space in which to carry the payload and crew, stability, enabling the aeroplane to naturally continue in the same direction, control, to change the aeroplane's direction and position in the air, and a force, thrust, which can propel the aeroplane forwards for the required length of time. These are therefore the 5 primary requirements that must be met by all powered aeroplanes. To meet these basic requirements, all powered aeroplanes have the same primary components. These components are the wings, which generate lift, enabling the aeroplane to fly and remain in the air, the fuselage, which safely carries the payload and crew, tail surfaces, which are designed to give the aeroplane stability, ensuring that the aeroplane naturally flies in a constant direction, control surfaces, to change the direction of the aeroplane's flight and, when required, its position in the air, and engines to produce thrust, propelling the aeroplane forwards for the required duration of the flight. The 5 primary requirements of an aeroplane are therefore met by these 5 primary components: the wings, fuselage, tail surfaces, control surfaces, and engines. Although all powered aeroplanes have the same primary components for flight, we notice that the actual design of these components is quite different. Looking at one component, the wings, they may be mounted at the top of the fuselage or close to the middle or towards the bottom of the fuselage. The wings may be straight and perpendicular to the fuselage or be swept backwards, be angled upwards towards the wingtips, which is called dihedral, downwards towards the wingtip, which is called anhedral, or be straight with no slope. Each aeroplane type has a combination of the wing designs outlined above. The actual wing design depends on the aeroplane's role rather than artistic style. A design feature that enables an aeroplane to fly faster will also have disadvantages. Similarly, a wing design that enables a heavily laden aeroplane to take off and land from a relatively short runway will have different disadvantages. Ultimately, every wing design is a compromise. Similarly, the design of the other aeroplane components is also a compromise. Notice how the fuselage, tail surfaces, controls and engine type and placement differs between the aeroplanes shown on the screen. These 3 aeroplanes, the now retired Concorde, the A340 and the PA-28, all have very different designs. Let us now consider how the design of the primary aeroplane components varies between these aeroplanes. Notice the different design of the wings, their shape and position, the fuselage shape and cross-section to length, the size, shape and presence of tail surfaces, the variation in size and location of control surfaces, and the location and number of engines. Study and consider the very different component designs of these 3 aeroplanes. Each design has advantages and disadvantages, and the final design is a role-centered compromise. Look for and consider these differences before moving on. At the beginning of this lesson, you were introduced to lift and thrust as 2 of the primary requirements for a powered aeroplane, the others being stability, control, and space for the payload and crew. We will now look at the 4 forces acting on an aeroplane whilst flying and their fundamental relationship. Whether on the ground or in the air, an aeroplane has mass, which due to the acceleration due to gravity results in a force, weight, which always acts or pulls the aeroplane vertically straight down, and weight increases as the mass of the aeroplane increases. When the aeroplane is on the ground, the surface provides a reaction, which equals the aeroplane's weight. The aeroplane is supported by and does not sink into the paved surface. However, when the aeroplane is in the air, the reaction from the ground is no longer present, and to prevent the aeroplane being pulled vertically down towards the Earth's surface, a force, lift, must be produced. This lift force must equal the force of weight if the aeroplane is to fly level. And the heavier the aeroplane, the greater the size of the required lift force. However, whenever there is relative motion and/or lift is produced, there will always be a force, drag, pulling backwards on the aeroplane. And the greater the lift, the greater the drag. In level flight, this drag force would slow the aeroplane down. If the aeroplane is to remain at the same speed in level flight, the drag must be balanced by a force, thrust, pulling the aeroplane forwards. We can now see that all four forces are related, and if an aeroplane is to fly level at a constant speed, a heavier aeroplane will require more lift, produce more drag, and therefore require more thrust. Similarly, a lighter aeroplane will have smaller lift, drag and thrust forces to maintain the same speed in level flight. To summarize, all powered aeroplanes have the same requirements, which are provided by the same aeroplane primary components. But the design of these components varies between aeroplane types. It is the role, and therefore the requirements of the aeroplane, that determine the design of these components, and that design will always be a compromise. Finally, we introduced the four forces acting on an aeroplane in flight, and saw that these forces are related. The forces lift, drag and thrust will be greater for a heavier aeroplane and less for a lighter aeroplane.